In the last class, we started discussing turbo machinery. So in that process, we discussed about different types of turbo machinery like pumps and turbines, and then we started discussing about pumps in particular. So there are certain parameters which we discussed for the pump, like net head, and then what is net head? That is the basically the energy which is the sum of static part, dynamic part, and elevation head at the outlet of pump minus the sum of energy at the inlet of the pump. So that is the net head which is imparted on the fluid due to the pump function. So that is also equal to energy grade line at the outlet minus energy grade line at the inlet. And if the changes in velocity and elevation they are negligible, then the above equation can be written P out minus P in divided by rho G. So it means that we are taking V out is equal to V in and that out is equal to that in, which is not the case always, but for the simplicity, we are just writing it that is the case. Then the net head which is being imparted on the fluid, that would be equal to the static outlet pressure and the outlet of pump minus static inlet pressure at the inlet of the pump divided by rho g. Okay, and then because this is head, so it would be in feet or inches or of the fluid. So that H is the height of the column which is shown here. So we can measure it always in feet or It depends on the fluid we are using in the pressure measuring device like manometer or whatever we are using it. Right, and energy grade line is at the inlet, that is equal to this, and energy grade line out is this. So difference between grade line at the outlet of the pump minus energy grade line at the inlet of the pump, that would give us the net head which is being imparted on the fluid. So then we discussed about the water horsepower, then that is the brake horsepower which is given by the electricity, and this water horsepower is the actual power which is delivered to the fluid. So because there are some frictional losses, so brake horsepower would always be greater than the water horsepower, and that ratio of water horsepower and brake horsepower, that is the efficiency of the pump. So as we discussed in the last class as well, that we can also take it like isentropic efficiency as we discussed in thermodynamics, right? So because that also kind of includes the frictional effect, so accommodates that, right? So it means that the actual pump work would be less than the ideal pump work which is being delivered by the shaft. So then we discussed about the pump performance curve, that we can have zero efficiency at 2 point. Let me show you the diagram, maybe it would be easier. So, okay, so this was the diagram that efficiency is zero as when we have got a shut-off head. Shut-off head means that we have switched on the pump, but at the outlet of the pump we have closed the valves. Then it means that there wouldn't be any volume flow rate, but the head which is available, the potential of that head is maximum. But because there is no volume flow rate going through the pump, so it means that efficiency would be zero. It means that there is no useful work that pump is doing. And then there is another extreme, that when we have got maximum volume flow rate, but the head which is imparted on the fluid, that is zero. It means that that pump function is not doing anything for to increase the net head of the uh, net head of the fluid. So it means that it is kind of a free delivery. So it means that it doesn't matter that if we put pump there or not, it would give us the same volume flow rate. So that is also of no use, because at that limiting case as well, as pump is not doing any work, so efficiency would be zero. So the point where we have got the maximum efficiency, this green line is, as I discussed on the whiteboard as well in the last class, that this green line, the maximum of that green line is the best efficiency point. Best efficiency point where the efficiency of the pump is maximum. So it means that for a given impeller diameter pump, we would have a volume flow rate at which that pump would give us the maximum efficiency, right? So this that head, that is the head which is available to us, right? But then there is another head which is required by the system. So, okay, now this blue line here, as I discussed in the last class as well, that it shows the net head which is available for the fluid to have, right? And it, yes, any question? Okay, maybe it was by mistake. So we just focus on the discussion in hand. So available head is the net head which can be gained by the fluid. But if you can see that if we increase the volume flow rate, the available head decreases. So it means that at the higher flow rate, the pressure increase in the fluid would be a little bit less. So that is intuitive. We can see that if the volume flow rate is more, then the pressure which is the outlet pressure of the fluid would be a little bit less as compared to the case when we have got low volume flow rate. Okay, so that was the available head. There is another curve here which is required head of the system. So that head of the required head being that the losses during the piping system and due to the component. So these are the losses which we also covered in chapter number 8, which was internal flows. If you remember that discussion and calculation of major head loss and minor head loss in that. So major head loss was due to friction that was equal to Fl upon D, and minor losses was depending on that loss coefficient Kl for each component in the piping system. So if we increase the volume flow rate in that case, so frictional losses and those minor losses would increase, and you can see it from the this red curve, and we know that if we increase the velocity, that drag would also increase inside the pipe. So the point where these two headlines intersect, that is actually the operating point of that pump. So for that for a given diameter of the impeller diameter and rotational speed. So for each rotational speed and diameter of the pump, there would be only one operating point, right? So it means that if we have got a pump of diameter like what you say, like 6 inches diameter. Just let's suppose that we have got 6 inches diameter and the RPM is 300, then there would be only one operating point. So if we switch on the motor, it would give us this volume flow rate. But as an engineer, what is our task? That we need to select a pump having such impeller diameter or rotational speed that this operating point is close to best efficiency point, so that it would give us the maximum efficiency for the arrangement, right? So that is, as an engineer, it is our task to do in industry. So we this available head, that is something that we can calculate, or it is usually given by the pump manufacturer, and as required, we can calculate by the consideration of major losses and minor losses. And we are going to do one numerical problem after this discussion, that how to calculate these things and see that whether the pump selected is in the acceptable range of the volume flow rate. So maybe 5 to 10 minutes time we will do that numerical, right? So this point should be so as an engineer, or for the best performance, if we can select a pump in which the operating point is closest to the best efficiency point, then that would be the ideal condition for us, right? So I had told you that why available head decreases and required head increases. So just a minute, please. Hold on. Okay, sorry for the interruption. That was an option call which I had to take. So, okay, so we were discussing the available head and required head before this break. So, as I discussed that required head can be calculated by the difference in pressure, by the difference in pressure at the outlet and inlet and the velocity difference, elevation difference, and then HL total, which is the total head loss for that piping system. We all know that this total head loss comprises of two parts. One is major loss and one is minor loss. So the available head can be matched with the required head by altering the volume flow rate. So it means that if we can change the volume flow rate of the piping system, we can kind of we can match it by, with the available with the required head. Right. So the most common situation is that an engineer selects a pump that is somewhat larger than the actual required, and then we can always reduce the volume flow rate by the use of some kind of valve or damper which is installed in the line. So it can be reduced. So it is always wise to have a pump having uh, 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 higher specification in terms of volume flow rate, and then that can be then that can the volume flow rate can be adjusted by the use of some valve, right? So it is common practice in the as I discussed that impeller diameters they are variable in a pump. So it means that a pump comes with a different impeller diameter. So it means that on the shaft of the pump we can adjust, we can have different impeller diameters. So advantage of doing that is manufacturing cost, because if we kind of offer pumps having different impeller diameters, separate pumps, it would cost more, and then it enables capacity increase by a simple impeller replacement. So if we want to increase the capacity, we can simply take out the low diameter impeller and then put the higher diameter impeller, and then installation mounting they are kind of same for a particular pump, and then we can reuse the equipment for different applications. So if I show you the available head for different uh, impeller diameters. So you can see here D1, D2, D3, D4. So here diameter D1 it is the smallest impeller diameter, and D4 is the largest impeller diameter. And then there are certain curves, green curves you can see on this graph. They are contours of the uh, constant efficiency for the pump. So it means that in this region here, we would have, if we are using D4, then in this volume flow rate, we would be having kind of 80%, 80% efficiency of the pump. And similarly, 70% efficiency of the pump control is shown, and then 60% they are kind of shown. So we usually show the constant efficiency curves on the same graph. So if I show you the performance characteristic for a pump manufacturer which is called TACO. So TACO Incorporation. This graph. Let me make it a little bit more clear to you. So here you can see different curves. One is these blue lines, they are those available heads for different diameters. Right here it is 12.75 inches, then 11.25 inches, then and 9.75 inches, and different blue line. And then we have got brake horsepower red lines which are shown here, and then these curves, green lines, they are the same constant efficiency curves which were shown on the last slide. So it means that if we need to have, let's suppose that we want to have 400 gallon per minute, then we have got different options here. Either we can use this uh, lowest diameter pump or higher diameter pump. So which would be good in this case? If you look here, that if we use this curve, then the efficiency would be lesser. If we use 6.75 inches diameter, pump, then the efficiency would be less than 50%. But if we move on to use like this impeller diameter, which is 12.75 inches, the pump efficiency would be around 78 to 80%, which is very high. So now you can a little bit easily see that what is the job of an engineer when you work in a design industry where you need to select a particular pump based on the market available pumps in the market. Then you kind of look at the performance curve, keeping in mind the efficacy for a particular efficiency ranges for a particular pump. And then first of all, we need to know that what is the required volume flow rate through that pump in the piping system, and then what are the valid diameters which are available, and then we can kind of see that where we can get the maximum efficiency. At which valid diameter we would get the maximum efficiency, right? Okay, now there is another thing. We will talk about this NSPH in a minute. Maybe before we do that, there is a medical problem which we can discuss now. So a local ventilation system would and exhaust duct having a volume flow rate of 600 cubic feet per minute, or if we talk about in terms of SI system, this is 0.283 meters cube per second, is used to remove air whose viscosity and density is given to reduce by a dry cleaning operation. Right, so there is a hood, there is a damper to control the volume flow rate, and there is a fan, which if we talk about, we just call it a type of a pump because it can also provide energy input to the system. And then there is a piping, and then here the air which is coming up through this hood that is going out into the atmosphere. Right, so now the duct is having a roughness of 0.15 mm. So epsilon value is given, and it is constructed of galvanized steel with longitudinal seams and with joints every 30 inch, 0.76 meter. Inner diameter of the duct is given 9.06 inch, and the total length is 44 feet for this. And then there are 5 variables along each duct having loss of skill of KL value 0.21. The hood entry loss of skill is 1.3. Yes. Anything? Any query? So then the hood entry length coefficient is 1.3, and the damper when it is fully open, that is 1. I think 8, which is not quite visible, but its value is 1.8. Now this is the data which is given for this ventilation system. So this is kind of exhaust system which usually we also kind of install this in our kitchen. So there is a hood, and then those humid air that is being taken out of the steam taken out of the kitchen as well. So, but here we are talking about ventilation system. So now that centrifugal pump, centrifugal fan that is installed here, that has because we are talking about the air that so that is why we are talking about fan. Otherwise, we usually use pump for the liquids, right? So a centrifugal fan with 9-inch inlet and outlet diameter available, its performance data is given. So at available data is given to us. So now at available data is given, and then determine the operating point of this local ventilation system based on the fan data, which is the operating point can be determined by plotting of required and available head and function of volume flow rate. Is the chosen fan adequate? So we need to find that whether it is adequate, and so we have been given available data, but we need to available head data, but we need to, if we go back a little bit, available data curve is given as a function of volume flow rate. All we need to do is to get this curve, right, which is this a red line. So it means that at different values of volume flow rate, we need to get the value of H required. Now, H required, how can it be calculated? That is the formula for this. P2 minus P1 upon OG plus P2 squared minus P1 squared upon 2G plus Z2 minus Z1 plus HL total, right? So now that is being done. the calculation we are going to perform only at required calculation we are going to perform, but we are going to perform it at only one volume flow rate value, and it needs to be done at different volume flow rate to get this curve, right? And we will come to that in a minute. So let me show you the curve which has this data that is given to us, and the next data, if you see here, that this is the data which is this that curve needs to be determined. So it can be determined by using different calculation of H required at different volume flow rate, right? Like at 200 cubic feet per minute, 400 cubic feet per minute, 600 cubic feet per minute, and 800. So we can kind of get this. And then when we do this calculation at different volume flow rate, we can draw this curve and we can find the intersection point of available head with the required head. Now, the volume flow rate for a given pump that is given to us, that we need to, that as in this data they have told us that the volume flow rate of that pump for that better diameter, that is 600 cubic feet per minute. So it means that the intersection point, which is the actual operating point, it, it should be on the right hand side of the volume flow rate, because if the intersection point is on the left hand side of the volume flow rate at which we want to okay, let me show it on the, now let me share it on the whiteboard, maybe that would be easy. So I'm going to share my, so as in the problem data, if you see that this data is given as available, if I show it here, that is this line. This line is given to us by the manufacturer, right? So this is the H available. Now we need to construct this H required line. For that, we can use different volume flow rate values like this one, then this 400, 600, 800, and then we can have 4 points and we can join it by curve fitting. And then we can find the intersection point of this available head line and required head line. And if you see in the data as well, that we have been given that we need to run this system at 600 cubic feet per minute. So after after the construction of this H required line, if the intersection point, which is this, if it is greater than this line, this line is the operating volume flow rate of this red line. Maybe that line is not the best line, so maybe I need to use green line. So, so this is the kind of operating volume flow rate for this assembly. So the intersection point should be greater than that. Otherwise, we are not getting the required volume flow rate. So I mean to say that if this curve is something like this, for instance, that if the H required curve is rainbow color, so if H required line is like this, so that intersection point is this. In that case, because if the desired volume flow rate is not going to be achieved by this pump, so it means that we cannot use this pump. So we need to have a bigger impeller diameter pump in which this curve would be high, even higher, right? So we need to make sure that the intersection point of available head curve and required head curve should be on the right hand side of the given volume, desired volume flow rate for that system, which is 600 cubic feet per minute in this case. Now, the question comes that how to do the calculation for this H required. So for that, let me copy this figure. By the way, this is example 14-1 for the Singer's book. So at the moment we are following Singer's book, which is 14-1. This is the example number 14-1 in that Singer and Imbala's book. So so this is the assembly we are talking about. that on which we need to calculate H required at different volume flow rate. So that we can construct this line, which is which was shown previously. Which line I am talking about? Let me see. This is that line. We need to construct this line. So we can construct it by calculating H required at different volume flow rate. Now, how can we calculate H required? That is by using this relation. So let me copy it again rather than write it. So we can just copy it from here. So here we can. So this is our equations on which we need to have different values in this. So if you see here that 1 is the point far away from the hood, so it means that we are talking about stagnation here. So it means that V1 would be equal to 0. Okay, before that we need to have P2 and P1 values because P1 is atmospheric because it is far away from that. So P1 is atmospheric pressure. So we can write P atmospheric. And then what is the value of P2? If we say that P2 point, because the jet is going out in the atmosphere, which is stagnation air. So P2, if we talk about the hydrostatic variation, then it would be P1 minus, it would be P1 minus rho into G, which is gamma, into Z2 minus Z1. Right? Because we are taking point 2 and point 1 as a as stagnant air. So it means that if it is stagnant air, then we can use the hydrostatic variation of pressure. Now V1 would be equal to 0. Why that? Because we are talking about far away from the hood. So V1 is equal to 0, and V2 would be equal to V velocity, which is here, right? And so then Z2 minus Z1, we can just put in the values. If we put the values here, H required would be equal to P atmospheric. So it would be P2 is equal to P atmospheric minus rho G, Z2 minus Z1 divided by rho G, and we would have also here, we would have minus P atmospheric, which is P1, and then plus V2 is equal to V, call it V square upon 2G plus Z2 minus Z1 plus HL major plus HL minor. Okay, HL major is fm upon G and HL minor as we discussed in chapter number 8. So you can see that all that calculation or analysis is going to be used here. So here if we do the cancellation, P atmospheric would go with this, rho G would be cancelled out with this, and then minus Z2 minus Z1 would be cancelled out with plus Z2 minus Z1. So now this equation has been reduced to H squared is equal to, it would be equal to V square upon 2G plus HL measure, if you remember, FL upon D into V square upon 2D, and HL minus that is plus KL into V square upon 2D. Right? So now H required for a given volume flow rate can be calculated by using this equation. So if we take V square upon 2D common, then we can just write it 1 plus FL upon D plus KL V square upon 2D. Now we need to do calculation at some volume flow rate. So as I explained here that in order to construct this line, we need to do calculation at different volume flow rate. So let's, for example, that if we do the calculation at this, because 600 cubic feet per minute is even so just for the analysis sake, if we do the calculation at that point, then it would be equal to, then we can just say, let me see that volume flow rate is if volume flow rate, if I show you that is 0.283 meters, right? So when volume flow rate is 0.283 meters, then we can just calculate the Reynolds number. So how can we calculate the Reynolds number for that? That would be equal to, if you remember that VD on nu, right? Okay, so what is the relation between velocity and volume flow rate? Volume flow rate is area, cross-sectional area into velocity. So velocity would be equal to volume flow rate divided by cross-sectional area, that is equal to pi by 4 d square. D is the diameter of the pipe. So this 4 would go here. So if we put that value here, then it would be equal to 4 volume flow rate divided by pi d square into d upon d divided by mu. Now, volume flow rate value that is given to us, that is 0.283 meter for this particular 600 cubic feet per minute, that is equal to that value 0.283 meters. So 0.283 divided by pi into, okay, so what is the diameter here? So diameter, inner diameter if you see here, the inner diameter of the duct is 0.23 kilometer. So that is the diameter value. So we just put it here, 0.23 square into diameter 0.23 divided by viscosity, that is also given in the data, which is 1.562 into 10 power 5. So it would be, Reynolds number comes out to be 1 lakh, 1 into 10 to the power 5. Now, once we get this, we also know epsilon value. So we can calculate epsilon. What is the value of epsilon in the data? It is having a roughness of 0.15 mm. So 0.15 mm is the epsilon value, and diameter of that duct is 0.23. So it would be 0.15 mm. So 0.15 mm into 10 to the minus 3 divided by diameter is 0.23. So epsilon upon d value comes down to be 6.52 into 10 to the minus 4. Now, by using this value and Reynolds number value, then we can use Moody chart or four group relations to find F, which is the friction factor for that pipe. So if we do that calculation as we did on several occasions in chapter number 8, so I hope that you can repeat, you can do the same calculation here. So if we do the calculation, then F value comes out to be 0.0209. So now we have got the F value. Now the only thing remaining is summation of Kn, which is the losses here. So the if you see that there are, again we see 1.3 is the entrance loss, then 1.8 is the dental loss. So those are the two straightforward. So first of all we write them 1.3 plus 1.8, and then what else here? There are five elbows. So if we see the chart for the elbows which are made of galvanized steel, the table, if we can find the value from there, then that value is 0.21, 5 into 0.21. So here value comes out to 4.15. Now, if you see in this at required one, that we copy it and then we paste it here. now we have calculated friction factor A and B scale. We can very easily calculate that in that would be volume flow rate divided by pi by 4 d square. So if we calculate that value of uh, velocity, that comes out to be 6.81 meter per second. So if we put in the value friction factor point 0.0209, and then KL value is 4.15. Length of the total length of the duct, what is total length? That is 44 feet, which is equal to 13.4 meter. Okay, so that is that, and then we have got all the things. So if we calculate as required, that comes out as required comes out to be equal to 15.2 meter of air. Right. So 15.2 meter of air. Now, if we look at the data which is given to us, that available data, it is given in inches of L2. So it means that this calculation which we have done in meter of air, we need to convert it into inches of water so that we can plot the data on the same graph. Right here, if you see that as unit are inches of H2 column height, that is in inches of H2. So for that calculation, that is quite easy, that we know that how to convert it. So as required in inches of H2O, that would be equal to H required meters of air. So it is meter of air. So meter of air can be converted uh, into inches. So that uh, and then first of all rho of air divided by rho of H2O, and then from meter to inches, if we need to convert it, that would be equal to 1 divided by 0.025 meter. 1 inch is equal to 0.0254 meter. Okay. We know that 1 inch is 25.4 mm, so that is 0.0254 meter. So if we put in the value 15.2, low of air, we usually take 1.18 or maybe 1, we can also take 1, and then low of I2 is approximately 1000 kg per meter cube, but in the book they have taken it 998 and into 1 upon 0.025. So if we do that, H required is equal to 0.709 in case of water. Now 0.709, can we see this value for 600? 600 what was the value again? 0.709. So 0.709. Where is that? If I can show you here, 0.709. This is 0.7. 709 means 71. So it is somewhere here. It is somewhere. This is the point, right? Similarly, we can find the points here at different volume flow rates, and then 1, 2, 3, and then we can add a point here, and then we can construct this stuff. So it means that you need to write a small program, or you can use an Excel sheet to change the value of volume flow rate and get the value of as required. So it is not very challenging. So we need to kind of get this value of as required for different volume flow rates. These available head data is always given by the manufacturer, right? Because they can conduct experiment and find the value of H available for different volume flow rates. But the H required, that depends on the piping system. So that cannot be given for the pipe. For the pump, the manufacturer provides the data. But how to use that pump in a particular piping system, that is our job. So it means that they cannot get this curve because they don't know the application. So it means that this H required curve we need to kind of come up with, so that we can find the operating point, and then we, because this operating point is on the right hand side of the planned mass flow rate, which was 600. So it means that this pump be quite would be quite suitable for our application. But if this curve comes somewhere here, then it means that it is not going to provide us 600 cubic feet per minute of air ventilation. So it means that either what we can do that either we can use a pump with a bigger impeller diameter. Then that would be somewhere it would be starting from here like this. So it means that maybe in that case it would be going to match here. So now you can easily see that if we change the impeller diameter to higher diameter, now it again kind of come on the right hand side. So that is the job of an engineer. In the industry where you want to select a pump for a particular application, you do all these calculations and you have to do multiple calculations, not one calculation as we shown here only for 600 cubic feet per minute. So you have to do it for maybe at least 10, 20 values. So it means that either you use some kind of program in C or Fortran or XML, so you can do anything you want so that you can find a suitable pump for a particular application. Right. So apart from that, in the last lecture slide, I also gave you this video. I hope that Hashir would have shared this video with you. It is just to show the general working principle of centrifugal pump. So let me now here we can see those blades of the impeller. This is the eye which I was talking about, impeller eye, that performance characteristic is on the impeller diameter, right? So this is the impeller diameter. And impeller eye, that is this impeller, right? So when we talk about impeller diameter, we are talking about this radius of these diameter of these blades. Okay, one thing we need to see here that here the fluid is coming in from the out of the water into this, right? If this is the suction side from where the pump is taking the water from the underground tank, then water would be coming from out of the boat into this, right? In the exit direction, and then from impeller it would go onto the impeller blade. Okay, suction side is the side where the pressure is lowest. So, because the fluid always travels from the high pressure, so it means that somehow we need to create a low pressure region at the impeller eye on the which is connected to the underground tank, so that water can be sucked in into impeller and then it go on to the next side, which is the pressure side. So this is the pressure side here. And the other side from where it is going out there is the this is the suction side and the outlet of the pump where it is going out there is the pressure side. So that's why sometimes we have to pour water into that centrifugal pump from that piping system so that we can have water here and so that enough negative pressure can be created. If there is no water here, then as the video said, that negative pressure would be negligible to serve the water. Now this is very important that if the pressure at the suction side, which is the minimum pressure in the pump, if that goes below the vapor pressure of the water, then what will happen? Then there would be some kind of bubble formation, right? And that bubble would kind of, when they are going to burst, when go toward the pressure side, then they would create a vibration or kind of wear and tear. So that phenomena is called cavitation. Okay, so more would be the suction head, lesser would be the. Okay, so it means that we cannot have pump response very high as compared to the this underground tank. Otherwise, this value would be very high, and it means that we need to have very low pressure air in order to tap the water. So that head, which is same for the operation without cavitation, that is called net section pressure head, and so net pressure section head. And yes. Okay, so that is enough. So we are going to discuss the net pressure suction head, which is the minimum pressure head at the suction side, which would prevent or make sure that there is no cavitation phenomena going to happen. So let me load it, and now with this introduction, as I have shown very clearly from this slide as well, that Uh, when pumping liquid, it is possible for the local pressure inside the pump to fall below the vapor pressure, as mentioned in the preview as well. So the vapor pressure is also called the saturation pressure, which you usually see from the steam table. Right? So you must have used steam tables in the thermodynamics. So the saturation pressure gives given temperature value and is listed in thermodynamics table as a function of saturation temperature. Yes, any query? Okay. So when the local pressure is less than the vapor pressure, then there would be some bubble formation, and those are called cavitation bubbles. So they are generally they are found on the suction side, because that is the point where we have got the lowest pressure, and on the other side we have got pressure side, where the pressure is going to be increased due to pump operation. So whenever we define the pressure, we usually define on the that net positive suction head, that is defined based on the suction side, not based on the pressure side. So how do we define the pressure side? The pressure side of the pump is the side where the pressure is more, and the inlet where the pump is being sucked into that pump, that is the suction side. After the cavitation bubbles are formed, they are transported to the pump to regions where the pressure is higher, like the region of this pressure side of the pump. So when the pressure would be higher there, what would happen to bubbles? They would blast, and when those bubbles would blast, then there would be kind of vibration, and it would cause wear and tear of these pump blades, pellet blade. So it means that that is not very desirable. So it means that we need to make sure that the pump operates well above this condition of cavitation. So how to make sure that that is made sure by the net positive section head and PSI. So to avoid cavitation, it needs to be ensured that the local pressure everywhere inside the pump stays above the vapor pressure of water at that given temperature. Right? Like at 25 degrees centigrade, what is the vapor pressure? We can see from the steam table. So we need to make sure that, and then secondly, the lowest pressure in the pump is on the section side, section inlet. So we define it at pump inlet, where the possibility of lowest pressure is there, because at section we have got the lowest pressure. So usually we calculate this net positive section head to see the possibility of cavitation. So it is defined as the difference between the pump inlet stagnation pressure head and the vapor pressure head. So stagnation pressure head at the inlet would be equal to P upon rho g, which is a static pressure head, plus dynamic pressure head, which is V scale upon 2D. minus PV upon rho G. Okay, from there to calculate this PV value, that is the saturation pressure at the working temperature of the fluid, which is water in this case. So if we are talking about at 25 degree centigrade, we can see go into the steam table, and at 25 degree centigrade, we can find the value of vapor pressure, that saturation pressure, which is PV. So this value should always be greater than zero, just to make sure that there is no bubble formation. So pump manufacturers, first of all, pump manufacturers test their pumps for cavitation. How do they do that? That they increase the volume flow rate. So when they increase the volume flow rate, then it means that they need more suction pressure and less pressure at the suction side, so that it can be sucked in with the higher volume flow rate. Right? So it means that this NPSH would decrease as this is the net positive suction head. It would decrease as we increase the volume flow rate. But there are two NPSS values. One is required and one is variable. So we are going to talk about both in the coming slides. So specifically, at a given flow rate and liquid temperature, the pressure at the pump inlet is slowly lowered until cavitation occurs somewhere inside the pump. So what do we do that? This P value, that is decreased at a given flow rate, and then it means that for that given flow rate, we know the value of NPSH. It means that if the that head is below that value, available head is below that value, then there will be cavitation. So the value of LPSH is calculated using the above equation and is recorded at this operating condition for different volume flow rates. So it means that, let me show you this figure, that when we increase the volume flow rate, then net positive suction head required would increase. Why it is being increased? Because at higher volume flow rate, the pressure at the section side would be lowered more. So it means that the net positive section head value should be more at higher volume flow rate. So the same thing is written here. The process is repeated at several other flow rates, and the pump manufacturer then publishes a performance parameter for the required net positive section head. So it means that let me take this figure on the whiteboard, then we can discuss it there. So the point where they intersect, that is the point that if we increase the volume flow rate from this point onwards, then because then the available head is less than the net positive section head, which is required to avoid cavitation, then it means that here we would see the danger of cavitation, because at the higher volume flow rate on the suction side, the pressure should be decreased, right? Only then the volume flow rate would increase, right? So that's why we need to make sure that we operate our pump on the left hand side of this intersection point to avoid cavitation. So it means that our operating point volume flow rate should be less than this intersection point, so that there is no cavitation. So this was the required net positive section head. And then there is another positive suction head which is available, right? So this is called net positive suction head which is available. Now, what is the difference between available head and net positive suction head? There are kind of a difference of vapor pressure of this. That because in the head calculation, if you go back, there is no mention of vapor pressure of fluid at a given temperature. But here in net positive second act, we have got this minus term here, right? So that's why they are kind of different values. And then net positive suction head required typically increases with volume flow rate. So that is the phenomenon we are talking about here. And what is net positive suction head? So this required net positive suction head that is being again provided by the manufacturer of the pump. But this net positive suction head available, that is again it is in our control that where we put the pump. So net positive suction head available, then again we need to calculate it from a particular application. So required data that is being again provided by the like this available that this head which was available here that was provided by the manufacturer, but the required head we calculated in the medical problem. Again here required NPSH value is given by the manufacturer and then available head we need to calculate. How to do that calculation? Let's see do that. So that is again we have written that on the second side of the pump, low pressures are commonly encountered as we discussed quite in detail. Also with the help of video, cavitation occurs when the liquid pressure is less than the liquid pressure, and this phenomenon is called cavitation, and it damages the pump impeller blades. So if we want to calculate the net positive second head, we need to subtract this. So this is the total head on the second side minus the liquid vapor pressure. So NPSH values, as I explained, that there are two values. One is the required net positive second head. So this must be maintained, or usually it should be higher than this required head. The available head should be higher than this net positive second head, so that cavitation will not occur as shown in this slide. So available head or available net positive second head should be greater than this required net positive second head. So required means that that value that is the minimum value required for a given flow rate so that there is no cavity. And what is actually there available for the system, that is NPSS available. Okay. So required head that would be provided by the manufacturer by conducting the experiments. But this available and net positive section head that runs the head that actually occurs for the particular flow system, which also has that consideration of height factor, that where we have installed, how much higher we have installed, because if the height between the second side and the pump and the water reservoir is more, then we need to have very low pressure at the section head to in order to suck that water into the pump. So that is kind of so that positive section head available that strongly depends upon the height of the pump where we are installing it. How it is what I meant to say with that, because if you see here that for the calculation of that positive section head available, there are these 2 points. This is the suction suction side of the pump here, and this is the storage tank from where we are kind of getting this. So it means that this is the red one. If we take this as a reference point, so it means that this is the height across which it needs to be traveled upwards into the section side of the pump, right? So applying the energy balance between the free liquid surface and a point on the suction side of the pump near the impeller blade, which is point 2. So we can say that we have got P atmosphere at this tank, then minus that one, right? So why it is minus? Because it is negative height. If we take this reference and if we go upward, that is positive height. Because it is less than this, so it means that this is minus that one. And then PS is the static pressure at this point 2 upon gamma, that is just to write it in terms of air, plus Vs square upon 2G, the velocity of water at the section side, plus HL. HL is the head loss between the free surface and the pump impeller. So it means that from here to here, how much length of the piping system is there that would have this HL, and that would have again two contribution. One is major losses, one is minor losses. Major losses is the friction losses in this pipe, and minor losses is due to this inlet and then this here 90-degree turn and things like that. Component losses, right? So from here, if we calculate this PS plus this stagnation pressure minus PS plus means scale upon 2G, that is equal to atmospheric pressure upon gamma minus that one minus HF, right? And then because in order to have net positive section head, we need to subtract minus PV upon gamma, which is the vapor pressure of the fluid at the given temperature, right? So now that because we have to subtract minus PV upon gamma, so we would do it on the left hand side as well as on the right hand side. The left hand side would become equal to net positive section head available, right? And the right hand side would be like this. Okay. So now if we want to, without doing any calculation, if we want, because in this figure, NPS available is on the higher side. So we want it to be as high as possible. That is required NPSH, that is that depends on a particular pump, and that is something we cannot change, right? Because that is depends on manufacturer, right? Yes, well then it's good. So we need to have this line as above as possible for the available net positive section, right? So how to do in this equation? If we see this equation, how can we increase that value? If this minus Z1, if it is Z1, if it is a very low value, then the subtraction would be less. So this value would be more. So physically speaking, if we can have this storage tank, it is above that, or maybe it is as close to this section side on the low side, or preferably if it is on the higher side, then there is this net positive section head available would be more and more. So that means that cavitation would be less. And then second thing, if we can decrease these losses in the piping system, which is from here to here. So it means that if we shorten the distance pipe between pump second side and the reservoir tank. But ideally, the best thing we can do is reduce height, or even if we can put it on top of the at higher altitude as compared to this pump. So that would remove any possibility of cavitation. And then what else we can do? That vapor pressure, if we can decrease it. How can we decrease vapor pressure? At a, for a given fluid. So if you remember that vapor pressure can be decreased if we decrease the temperature, saturation temperature. So it means that if the fluid is at a if the fluid is cold, then vapor pressure would be a little bit less. So in that case as well, NPS available would be more, and the possibility of cavitation would be less. So that is something which I have. So it is very important to know that these physical understandings, they are more important than the calculation we do in the numerical problem. Because numerical problem we just do just to demonstrate those physical understanding concepts, right? So please focus on these understanding of the concept, but the major emphasis on the should be on the understanding of the concept, design concept, that's how you can design a system in a better way, right? So as the height of the pump pellet plate above the fluid surface is increased, the NSPHA is decreased, right? So it means that if we kind of this at one height, which is increased, and then NPSHA would be decreased. So therefore, there is some critical value for that one above which the pump cannot operate without cavitation. So it means that we cannot. There would be some case, limiting value of that one. After which, if the water level is lower than that, then there would always be cavitation. So we need to make sure that that is not the case. And the specific value depends on the head losses and the value of vapor pressure. It is further noted that if the supply tank or reservoir above the pump, it means that here somewhere here, then what will happen? Then NPSHA will increase as the height is increased. So that one would be negative. So it means that it would add to this then, right? So I hope that you can understand this point. So for proper pump operation and net power suction head available should always be greater than the net positive suction head required, right? So I think if there is any question, you can ask now. Otherwise, we can do this medical problem in the next class. Maybe we don't have much time left. And okay, before we do any calculation for the medical, let us see this graph. Okay, so here this line, this line, this line is showing this upward line, which is increasing with the volume flow rate. That is the NPSH required line, which is being provided by the manufacturer of that pump. Now there are two lines here. One is NPSH at 25 degrees centigrade. So that line is a little bit higher than the NPSH available at 60 degrees centigrade. Right? So as I was mentioning here, that if here because PV upon gamma it is being subtracted, and PV value vapor pressure or saturation pressure of the water at a given temperature, it increases with the temperature. So you can see here that available head at 60 degree, that is a little bit lower as compared to available net positive suction head, which is available at 25 degrees centigrade. So it is of more advantage to us to pump the fluid which is at lower temperature, so that the available net positive suction head would always be having a higher value. So it means that if the water which is available up to 25 degrees centigrade, the safe volume flow rate for this pump is 600 gallon per minute. So if we increase the volume flow rate beyond that point, then there would be cavitation, because that is the cross intersection of that. But if the same fluid is available at 60 degrees centigrade, then you can easily see that the safe volume flow rate limit is only around 550 gallons per minute, right? So and those were the two lines which we need to. That is the effect of changing the temperature. So to summarize, if we increase the temperature of the working fluid, then vapor pressure increases and net positive suction head available decreases. So this line, which is net positive suction head required, that is fixed for a pump, and that is this curve is given by the manufacturer. So if I show you the Taco Incorporation's pump performance curves, here you can see net positive suction head required, right? So it is somewhere here. So, but for this they have shown it on a different scale. Here, if you see that that scale is starting from there, and that is 0, 2, 4, 6, 8, 10. And here, the value of head available, that is 20, 40, 60, 80, right? So now it means that this curve would actually be somewhere here, because we are talking about 0 to 10. So they should have shown it somewhere here, but for the clarity, they have shown it on the other side. And the scale which is going to be used here, that would be this one, 0, 2, 4, 6, 10, 8, 3. And if we plot it here, that would be somewhere from here, it would be somewhere here. Like this. So you can see that all the impeller curve, available head curve, they are greater than the NPSH, but they are the available head. They are not the net positive suction head. For that, we need to draw those curves as well, and then compare it with the required NPSH. Right? But just to give you an idea that available head is quite great. Like here, if the impeller diameter is 12.75 inches, then the available head is kind of more than 40 feet, and the net positive suction head is less than 10 feet. So there is no possibility of cavitation at all in that case, for a very large altitude difference as well. So but we need to draw those net positive suction head available curves as well to compare it with required net positive suction head. Right? So I hope that this chapter is more about the application. So you need to focus more on that how to do these selection of the pump, and how to make sure that we choose the best efficiency pump which gives us the required volume flow rate. So it all depends on the on these performance curves having these constant efficiency contours, as well as the consideration of this net positive suction head to avoid cavitation. So to avoid cavitation, the rule of thumb is that the elevation difference between the pump and the storage tank should be very less, and reliably, if this storage tank is on the upper side, then the cavitation would be practically impossible. Because then, in that case, this that one would be kind of adding this here rather than subtracting here, right? So I hope that this point is clear.